Welcome to probability class. Woo! All right. Before we start talking about how to compute probability, I just want to talk about a little problem. So some of y'all might have heard this before. It's a pretty common math problem. But for those of you who have not, hopefully we'll enjoy ourselves. So here's a question. So this is called the Monty Hall problem. So basically, Monty Hall was the host of a game show called Let's Make a Deal. And the classic problem says that there are 3 doors. Behind 2 of the doors are goats. Behind 1 of the door is a car. If you pick the one with the car, you win. If you pick the one with the goat, you don't get to keep the goat. They need it for the future games. But you do get to keep the car if you catch it. So, let's assume that you pick a door. So, does it matter, right? Probably not. So, you're going to pick door number 2. So since Monty is such a nice guy, he's going to say, well, let me show you what's behind door number 2. Sorry, you pick door number 1. Let me show you what's behind door number 2. There's a goat. All right, so now he turns back to the person and he says, all right, do you want to switch to door number 3? Or would you like to stay with door number 1? So the question to the Monty Hall problem is, should you keep your door or switch doors? So let's think about this for a second. Should you keep your door or should you switch doors? Or does it not matter at all? So some students would say it doesn't matter at all because it's a 50-50 chance now. Some people would say that you should definitely keep your door because, you know, instincts, right? Your gut said door number 1, you should stay with door number 1. Some people say switch doors because maybe he's trying to fool you into keeping your door. Maybe you should keep your door because he's trying to fool you into switching your doors. So what's the answer? There is an actual answer. And what is it? Let's talk about some probability and then we'll get back to this. Yeah, this is the way to keep students involved. Woo! All right, basic probability. So probability, we say, is the measure of the likelihood. The measure of the likelihood of a random phenomenon or chance behavior occurring. So in this class, when we talk about probability, we're going to be talking about it in its decimal form. So that would mean that 75% in the probability would be 0.75. 100% would just be 1, right? So if you notice, we're moving our decimal over 2 places. So if we move our decimal over 2 places, 100% is the same as a decimal of 1. And likewise, 0.3% would be not 30, but if you move it to the left, right, 0.003. So that's how we talk about probability. So probability also deals with experiments that yield short-term results or outcomes, yet reveal long-term predictability. So the long-term proportion in which a certain outcome is observed is called the probability of the outcome. So if you do an experiment over and over and over and over and over again, right, this long-term proportion, you keep doing it over and over again, you should get the probability of that outcome. And this is actually what we call the law of large numbers. So as the number of repetitions in an experiment increases, right, the more times you do something, the proportion, in other words, when you figure it out, right, the proportion with which a certain outcome is observed is closer to the actual probability of the outcome. So as the number of times you repeat an experiment increases, the proportion is going to be closer to the actual probability. That's a lot of words. What does that mean? All right, so let's look at this. If we flip a coin 1 time and it's heads, right? We flip a coin once and it's heads. Can we say, oh my gosh, that was 1 heads out of 1. This coin is 100% heads. It will never get a tails. Can we assume that? No, of course not, right? Well, what if we flipped it 3 times and it was heads? Oh man, that's 3 out of 3. 100% heads, right? Well, no, of course not. If you did it 4 times, let's say the next one was a tails. Can we assume 3 out of 4 times will be heads, 75%? No, right? The more times you do it, the closer it should arguably get to what we would expect. And on a coin flip, we would expect it to be 50%. So let's actually look at that. So here's a website that tells us the number of coin flips. So if we did 10 coin flips, right? Let's toss them. So this calculated that we would get 4 heads and 6 tails. So the ratio of that would be about 40% and 60%. So still not 50-50. So let's do 100 more times. So we flip 100 more times. All right, we get 52 and 58, which is getting kind of closer, right? That's 47%, 52%, right? We're just dividing by the total. If we did 1,000 more times, right? And we can let a computer do it. It's doing the exact same process as what we would be doing, as just flipping a coin, right? So if we look at that, oh, this is getting even closer, right? So the more times we do it, the more it's getting closer to this 50-50, to where this actually rounds off to 50-50. All right. Now we can actually do that with the Monty Hall problem. So we've established that the more times we do something, the more times we're likely to get the actual probability. So with a coin, we got 50-50, right? So if we do the Monty Hall problem over and over again, arguably we should be able to see what the real probability of it is. So let's just do it 10 times, and let's say we keep it. So if we keep our door, how often are we going to win? So according to this, we would have won 2 times and lost 80 times. But 10 isn't that great, right? So let's go 100 more times. All right, so if we did 100 times, or 100 more times, so 110, we would win 27% and lose, we would win 27 times and lose 83 times. But again, 100 isn't great, so let's do 1,000 more times. Let's do 1,000 more after that. Let's do another 1,000. So over 3,000, we're getting pretty close to what the actual probability should be, right? If we do 4,000, yeah, we're starting to see these percentages aren't moving too often anymore. So this tells us that if we, on Monty Hall problem, right, if we switch doors, so if it was the scenario where we had door number 1, we saw that door number 2 was a goat, and so we could switch to door number 3. What it says, according to this, if we kept it, we would only win 33% of the time. And if we switched it, we would win about 67% of the time, right? That's what this tells us. If we kept our door, we would win 33% and lose 67%, which means that if we switched it, we would have won 67% of the time. So for the Monty Hall problem, what's the answer? Should we keep it or should we switch it? Well, according to our law of large numbers, right, it looks like the actual answer is to switch. All right, that is all I need you to understand for this class. You do not need to understand any more. So if you would like to skip a little ahead, so when we are doing talking about sample spaces, feel free. But for those of us who are a little curious, let me explain why. So let's give a little more space. So again, if you don't want to understand this, if you don't understand this, totally okay. But here is the explanation for why you should switch. Again, not going to be tested on it. It does not matter. Just for those of us who are curious. So if we keep, so we have, at the beginning of this game, right, we have 3 doors. So what is the probability of winning our door? So if we get our door, we would win 1/3% of the time. we would lose 2/3% of the time. Now, the thing that happens, the guy opens the door and it says that there is a goat. So, because we started off with 3 doors, it's still the case that we would win with door number 1, or we would lose if we don't choose door number 1. Technically, we could still choose door number 2. It would be stupid because we know there's a goat, but just because we know there's a goat doesn't mean that these probabilities change. And actually, if you look at it, right, 1 divided by 3 is 33%, right? It's 0.333. And if you look at the losing, if you switched, it would be 0.667 or 67%, right? So it might not make any sense, but from doing this over and over again, right, from the law of large numbers, we saw that if we kept our door, it was a 1/3 chance of winning. And if we switched our door, it was a 2/3 chance of winning, right? So that's why, and again, if you don't understand that, that is totally okay. Mathematicians way smarter than us couldn't decide this for the longest time. But because we did this over and over again, right, just like with the coin toss, we can see that this is why it's the case. Very weird, but there you go. All right, so let's move back into our handout and let's talk about some sample spaces. So, sample space. In probability, we say that an experiment is any process with uncertain results that can be repeated. So the sample space, typically written as a letter S, of a probability experiment is the collection of all possible outcomes. So this is all of the possible outcomes for your experiment. And we use braces in our notation. So it'll look like this. So you'll put a little brace, you'll write all of the outcomes, and then you'll end with a brace. An event is any of these outcomes. Typically, an event can consist of one or more outcomes. We'll actually show what this means in a second. If we have a single outcome, this is called a simple event. And sometimes it's listed as E with a little I there. So an event is just one or more outcomes. A simple event, also known as an event, is specifically one outcome. Now again, this might seem a little confusing, so let's actually look at some examples. Example number 1. So you flip a coin 1 time. What would the events be? So you can flip a heads. Oop. Doesn't seem like my, all right, there we go. You can flip a heads or you can flip a tails. All right, so then what would the sample space be? So you have your braces. So if we use H and T, we have heads and we have tails, heads and tails. Those are the only 2 options, right? Cool. So let's do the next one. You flip 2 coins. So what are the events? So you can get 2 heads. You can get 2 tails. Or you can get 1 heads and 1 tails. All right. So what's the sample space? So if you use H and T's, we can have HH, heads, heads. We can have TT. We can have HT. Is there anything else we can have? Well, yeah, we can actually have TH. So what's the difference between HT and TH? So in HT, you would have tails first, or sorry, heads first and then tails. On TH, you would have tails first and then heads. So this tells you which order that you can have. So out of these, which one consists of, out of these original events, right, from number 1, from part A, which one consists of 2 or more outcomes? Well, we can see that 2 heads is just one outcome. We can see that 2 tails is just one outcome. But 1 heads and 1 tails, there are multiple ways of getting that, right? You could either get it as heads first or as tails first. So the one that has 2 or more outcomes is 1 heads and 1 tails. Which would mean that which of those outcomes, which of these are simple events? So remember, simple event means that it only has one outcome. Well, we said 2 heads only has one outcome, and 2 tails only has one outcome, right? There's only one way of getting 2 heads and one way of getting 2 tails. So 2 heads is simple, and 2 tails is simple. All right, so my pen seems to not work, so I'm gonna pause this video, get my pen to work again, and then we'll do part 2.